Hey, my friends, this is section 8.4, AP Calc 2, Comparison of Series. We have been learning different ways to sort out the series whose terms go to zero. Outside of this bubble are the series whose terms do not go to zero. Those are the nth term ones. They're outside of this. And then the ones that do go to zero, we have been learning different ways to determine do they converge or do they diverge. And we have a few different ways. We've got geometric, we have telescoping, we have integral test, we have p-series. And we are going to learn not really a new test today. It's kind of a new test. But basically, this one is going to allow us to really expand the number of series that we are able to sort into one of these two sides. So I'm going to start with an example, 1 over 2 plus 3 to the nth. Now this doesn't fit nicely into any of the molds that we have. I can't just look at it and decide, I can't say, oh, this is a p-series or this is geometric, because it doesn't fit any of those just right. I do know that the terms go to zero because the bottom is going to never stop growing, and it's growing exponentially, in fact. So the terms do go to zero. I'm still having a lot of mistakes with people trying to use the nth term test backwards. The nth term test says if the terms don't go to zero, then it's out here outside the bubble and it has no chance to converge. This is all diverge. Where the terms do not go to zero. People are still trying to use that backwards and say the terms go to zero, so therefore my series must converge, which is not allowed. You can say the terms go to zero, so therefore it has a chance to converge, so now I have to determine convergence or divergence with one of these tests, but it is not enough to say the terms go to zero. So in this one, the terms do go to zero, which lets me know that at least I can continue the process. Now, if I had given you this series, this direct comparison is a very useful and very easy test. If I'd given you 1 over 3 to the nth power, that's just another way to say the sum of 1/3 to the nth power, because the top would be 1 to the nth, which is always 1. So this is a geometric series. Its first term is 1/3. And its R value is also 1/3 because I multiply by an additional 1/3 every time. And I know that this thing converges because it's a geometric. It's a geometric, and R equals 1/3, which is between -1 and 1. So 1 over 3 to the n converges. What I want to do here is directly compare a term at a time, my current series that I'm working on, with 1 over 3 to the n. So think about, when n is 1, how do 1 over 2 plus 3 to the n, actually when the n is anything, how do these two things compare? If I throw an additional 2 on the bottom of one of these two formulas, how's that going to change it? If I throw 2 on the bottom, is it going to make it bigger or smaller? And the answer is, by making the denominator bigger, you always make the term smaller. So for any n value in the world, starting at 1 and counting upwards, you will make these terms smaller by putting an additional 2 in the denominator. So what I know is that my first term is less than 1/3. It's actually 1/5. My second term would be 1/9 without the 2, but since I put the 2 in, it's 1/11. My third term would be 1 over 27, but it's 1 over 29, and so on. And each one of those terms that I just wrote are less than its counterpart in the geometric series that I do know about. So, conclusion is, less than converging also converges. I can even add this one up. It's geometric, so I could find its sum. I'm not going to do that right now because that's not the point, but I do know that it converges to some finite amount. It doesn't add up to infinity. And I know that my current series is smaller than it, so that it converges as well. So the way you would want to phrase your answer, we also need to work on answer phrases. You need to say that you are doing a direct comparison to the series you want to compare to, which for us is the sum from 1 to infinity of 1 over 3 to the n. Now you need to say what you know about the one you're comparing to, and that's that it converges because it's geometric with r equal to 1/3. So I said what I'm comparing to. I said what I know about it, that it converges. So I'm doing a direct comparison to it. Therefore, the series I'm working on converges also. Because, and this starting inequality would be the start of your answer. And it doesn't have to be exactly like this every time, but you do need to get all this info in there. You need to say, I'm comparing it to this series. I know that I'm always less than this series, and I know that this series converges. So if I'm always less than, every single term is less than a convergent series, then my series must converge also. All right, this is called direct comparison, and it's very useful to compare to p-series and to compare to geometric series. Okay, so the next test is a sort of a form of this one, and it's called the limit comparison test. This comparison test is useful when you can't quite make a direct comparison. And the rules of the test are this. If two different series, A and B, and A sub n and B sub n are the formulas for each of those series. If both of them have all positive terms, and the limit as n goes to infinity of A sub n over B sub n is equal to a finite positive number, then both A and B converge or both diverge. Okay, so unfortunately this one's not quite as simple as a direct comparison where we just say something like, oh yeah, this one diverges and I'm always bigger than it, so I must diverge too. I don't really think I really said that on part one, but if you're smaller than converging, you converge, and if you're bigger than diverging, you diverge. So hopefully you extended that in your mind already. Limit comparison, a little bit more complicated, but just know that you're going to use it when you can't quite make direct comparison work. And it works for, to quote your book, the limit comparison test works well for comparing a, quote, messy algebraic series with a p-series. So if you get a, quote, messy algebraic series, and it's got basically a rational function with a polynomial on the top and a polynomial on the bottom, you're probably going to compare it to a p-series to make this test work. Here's an example. 5n minus 3 over n squared minus 2n plus 5. Here's where it's real tempting to say, wait, the bottom's squared and the top is not, so these terms approach 0, so it must converge. The terms do go to 0, but that doesn't mean the series goes to 0. I just keep stressing that because it's the same issues every year. People want to use that nth term test backwards. Don't do that. So what you want to do to choose what to compare it to. You want to compare it to a p-series, and what you do is kind of take the biggest degree. My largest degree on top is just n, and my largest degree on the bottom is n squared. Ignore everything else, and then reduce this. This reduces to 1 over n. If you take those biggest degree terms, ignoring the coefficients, and just look at the ends and then simplify n over n squared down to 1 over n. This is what you want to compare to. So if you're going to compare to it, you need to know about it. So hopefully you're thinking, what does 1 over n do? I'll give you a second to think about it. And it diverges. It's the harmonic series, which we've talked about. It's a p-series with p equal to 1. That's the cutoff point. So this diverges. So if I can take this limit that I talked about above and get a finite positive number as my answer, then I know they both act the same way. And since the one I'm comparing to diverges, I will know that my series diverges as well. Okay? So this one, not quite as simple, like I said, but I just need to put a sub n over b sub n, which is just the two formulas, one over top of the other. And the one I'm comparing to, the one that I know about, is 1 over n. I'm going to take all of that mess and take the limit of it and see what I get. All right, it looks pretty bad right now, but we'll fix it up. The limit as n goes to infinity of 5n minus 3 over n squared minus 2n plus 5 times n over 1, because dividing by 1 over n is the same as multiplying by n over 1. Okay, so if I multiply the top, I get 5n squared minus 3n, and the bottom is not going to change, n squared minus 2n plus 5. And this limit, since my bottom and top are both squared, is just 5 over 1. Everything else is meaningless. You know, all of this ignored, doesn't mean anything in terms of finding the limit. And my answer is just 5. So now, don't say that your series converges to 5. Just use the test and use the conclusions that you can make. The test says, if this limit, which I just found, turned out to be a finite positive number, such as 5, then a sub n and b sub n either both converge or both diverge. So I basically know that they act the same way, speaking of convergence. Therefore, the series I've been working on, which is this one, diverges by limit comparison. And that could be your answer. And the work above would be part of your justification. All right, so why not just do a direct comparison? In order to do a direct comparison, you have to be able to show a term at a time that every single term is less than or every single term is greater than the one you're comparing to. So I can't show that. I could maybe try to do a direct comparison to some sort of n over n squared or something like that, but it just doesn't fit. It's more complicated than that. So choose a p-series, do this limit of the one formula over the other formula. This right here would be an, and this would be bn. And if you get a finite positive value like 5, then you know they both act the same way. All right, so that's limit comparison. So you got two different parts of this section. Direct comparison, which is quick and easy. Limit comparison, which takes a little bit more work if you can't make direct comparison work. But we just really increased the amount of series we can sort into convergence or divergence. So I'll see you in class. I hope you've enjoyed 8.4. Just to keep you aware, we're going to be cutting this chapter off after 8.6. So a couple more sections, and then Eight five is an easy one, and then 8-6 we'll probably spend a couple days on, and then it'll be time to review and have our second big test. So I'll see you in class. Young out.